Welcome to The Explainer. I am absolutely thrilled you're joining me today, because we are going to unpack a truly mind-bending reality. Seriously, we're going to explore how a series of mathematical breakthroughs from the 19th century are currently powering the bleeding edge of artificial intelligence interpretability. We're literally bridging the gap between historical chalkboards and modern silicon.
Now I want you to ask yourself a seemingly impossible question. Can we peer into the silent workspace of a frontier language model like Anthropic's Claude and actually see what it's thinking before it speaks? Is it possible to map the invisible, latent concepts swirling around inside an AI's neural network?
Okay, let's dive into this. Here is our roadmap. 1. The modern AI mystery. 2. Meet the master of math. 3. The Jacobian matrix explained. 4. The Hamilton-Jacobi equation. 5. Elliptic functions and identities. And 6. A legacy written in silicon.
Section 1. The modern AI mystery. Peering into Claude's silent workspace.
Imagine we're in the year 2026, and AI researchers are intensely focused on a massive challenge. They aren't just trying to make models smarter anymore. They're trying to audit the private internal states of these models to ensure they're actually safe and aligned. This single line of code published on Anthropic's GitHub is the mathematical key. What's really interesting here is how a vector from a hidden layer inside the model, that H right there, is multiplied by a matrix, the J, and then unembedded. It's a linear transformation that decodes a model's hidden layers into a ranked list of human-readable vocabulary.
So that code powers what we call the Jacobian Lens, or J-Lens. This is an incredible interpretability technique that maps internal activations into word-like readouts. And by doing this, researchers discovered what they call the J-space, which is a small, internal workspace that actively shapes Claude's reasoning. But here's the truly awe-inspiring part. The concepts firing in this J-space often never actually appear in the AI's final text output to the user.
This creates a stark, fascinating contrast. The J-Lens basically allows researchers to separate what the model is thinking from what it's saying. When a pattern for a word like manipulation activates in the J-space, it doesn't mean the model is saying that word out loud. It simply means that concept is available as reasoning material. It is a functional analog of conscious access captured purely in math.
Section 2. Meet the master of math, Carl Gustav Jacob Jacobi.
So where exactly did the specific mathematical architecture come from? Well, we need to solve a bit of a historical mystery. Meet Carl Gustav Jacob Jacobi. Born in Prussia back in 1804, this guy was an absolute giant of mathematics. In 1829, he publishes a groundbreaking treatise on elliptic functions. By 1841, he popularizes the standard symbol we use for partial derivatives today. He passes away in 1851. Yet, skip all the way forward to 2026, and his foundational theories are actively unlocking the black box of artificial intelligence. It's an unbelievable bridge straight across the centuries.
Jacobi's interests were remarkably broad, which is why his name pops up across so many different fields, honestly causing a lot of serious confusion. Let's use a cognitive map here to sort the mental clutter and strictly disambiguate the four major frameworks that sound so incredibly similar. We've got the Jacobian matrix in multivariable calculus, the Hamilton-Jacobi equation in mechanics, the Jacobi elliptic functions in trigonometry, and the Jacobi identity in algebra.
Section 3. The Jacobian matrix explained. Sensitivity and rates of change.
Focus on the first pillar. This is the exact mathematical engine powering Anthropic's new tool. The Jacobian matrix is essentially a giant grid of sensitivities. Because neural networks process billions of parameters, researchers need to know if we slightly tweak one tiny internal activation, how does that change what the model might say later? The Jacobian captures that exact rate of change, perfectly mapping out the input-to-output sensitivity.
So, the crucial point here is that this matrix acts as a first-order approximation. Inside an AI, concepts are fluid and continuous, right? But researchers need concrete data. The Jacobian matrix forces those continuous, messy associations of the neural network into perfectly explicit, readable data, translating internal states directly into standard vocabulary.
Section 4. The Hamilton-Jacobi equation. Mechanics is waves.
Now, stepping out of multivariable calculus and directly into the realm of classical physics, we hit a nonlinear partial differential equation. Before this, mechanical motion was largely calculated by tracking discrete physical points over time. But the Hamilton-Jacobi equation radically reframed all of that. By providing a necessary condition for finding extremal geometry, it allowed the motion of a mechanical particle to actually be represented as a continuous wave. This profoundly changed how we understand movement in space.
This brilliantly bridged the gap between the classical physical world and the bizarre quantum realm we study today. By treating particles as if they propagated like light, this equation fulfills a major 18th century goal known as Hamilton's optico-mechanical analogy. It literally represents the absolute closest approach of classical mechanics to modern quantum mechanics.
Section 5. Elliptic functions and identities, periodicities and Lie algebras.
Let's transition over to complex analysis. You know how standard trigonometry uses circles to calculate periodic movement? Well, Jacobi expanded this into entirely new dimensions. He mapped these standard rules onto ellipses, creating patterns so complex they repeat in multiple dimensions at once. They become doubly periodic in the complex plane.
Now, while that sounds highly abstract, this math grounds itself in incredible physical realities. Jacobi's functions actually govern the precise swing of a grandfather clock pendulum. They model the spin of Euler and Lagrange tops in gravitational fields. They even solve literal planetary motion in the Kepler problem. And today, engineers use them to design electronic filters for our modern devices.
To complete our map, we have the Jacobi identity. This is an unyielding structural rule, essentially the ultimate mathematical glue that ensures complex operator algebra stay perfectly sound. If you're studying vector fields or Hamiltonian mechanics, this is the foundational property that keeps all the math structurally stable.
Section 6. A legacy written in silicon, tricking rocks into thinking.
Let's bring this all back to the present day to see how this legacy is quite literally written in silicon. When anthropic researchers used the Jacobian lens to peer into the AI's internal workings, they empirically observed a strict bottleneck. They found a maximum of about 25 J-lens vectors meaningfully active at any one time. Geometrically, this creates a 25-dimensional cone of thought representing the active J-space inside the model. Just 25.
So how do we capture those 25 dimensions? We use what researchers call a semiotic bridge. We often joke that computing is really just tricking rocks into thinking using lightning and text. But it is absolutely mesmerizing that Jacobi's 19th century mathematical formalization acts as the unyielding logic gate doing the tricking. His equations allow us to strictly map the swirling, continuous probabilistic associations of a language model into deterministic, observable, human-readable text on a silicon substrate.
We are building the most advanced technology in human history, actively mapping the internal consciousness-like workspace of artificial intelligence. But if the exact tool we use to do that relies entirely on 19th century algebraic geometry, is the ghost in the machine really just Jacobi's ghost? It is incredible to see how historical mathematical architecture completely defines our modern digital frontier. Thank you so much for joining me for this explainer, and I will catch you next time.